Welcome to EET3329C, Communication Systems at Valencia College. This is your lecturer, Dr. Wilfredo Rivas Torres. For lecture number 2, we'll be covering signals and signal space. Our agenda for today, for part 1 of our lecture at least, we will talk about the size of a signal, classifications of signal, some useful signal operations, the unit impulse function, and signals versus vectors. For part 2, we will talk about orthogonal signals, correlation of signals, Parseval's theorem, trigonometric Fourier series, and the exponential Fourier series. So let's get started. So systems. Let's talk. Signals are processed by systems which modify the signal to extract information from within. Think about an anti-aircraft missile. You may want to know if there's a hostile target moving towards you and which is being tracked by your radar, right? So the operator always wants to know where it is and at what velocity is this missile moving, right? So that's the information that we're trying to extract from the signal. So you need to properly process the signal so that you can estimate what the target trajectory is, right? Um, so the definition for a system is it's an entity that processes a set of signals or inputs to yield another set of signals or outputs, which is very similar to what we were talking about in uh, our first lecture, the message, which is the thing that we want to send through the system, and we want to be able to extract the message on the other side. This is just another way of looking at it or talking about it. Now, systems can be anything, right? They can be physical components, as in electrical, mechanical, hydraulic systems. In other words, the hardware realization of the system. It could be things like computer modules that computes an output signal from whatever the input was, right? So most modern systems are a combination of both the physical and software components. Now, we can't talk about signal size. So when we talk about signal size, many people think, oh, it's the strength of the signal, right? So let's say that our signal changes or varies with time, right? So why would a signal that varies with time, right, um, exist measure how can it be measured by a single number? Something that we could call either the signal size or the signal strength, right? Uh, Such a measure we can think about as the amplitude, but also its duration. That's the sort of things that we can measure from a signal, right? So we really want to measure a signal in terms of its strength, and we actually talk about the signal energy and the signal power, right? Remember that in order for a signal, as we talked about in lecture 1, to overcome the channel uh, distortions and losses and that sort of, it needs energy, and it consumes energy over time, and energy over time is what we call power, right? So we want to always make sure that our signal starts off with enough power so it can reach the receiver. Remember in lecture 1 we talked about uh, Fritz's equation, right? In order to get from point A to point B, you need to start out with a certain power so that by the time you get to the receiver, you have at least the minimum signal that you need. So talking about this, let's do an example. We haven't done an example of Fritz's equation. Why don't we go ahead and do that? So let's say we have a system that's operating at 1800 megahertz. For those of you who are keeping tabs, that's also 1.8 gigahertz. Let's say some kind of cellular environment, and we have antenna gains of 5 and 3 dBIs. Now, dBIs is a unit that we use to talk about antenna gain, and it stands for dB isotropic. So comparing it to an isotropic antenna, that's a detail not super relevant to this course, but I thought I mentioned it. So it is required to determine the minimum transmitted power in order for the base station to serve a mobile that's 1,000 meters away, but it is in line of sight, meaning that there's, like we mentioned again in the first lecture, there's no obstruction, nothing in between to block the signal. Now, receiver sensitivity, and when we talk about receiver sensitivity, that's the minimum signal for your mobile to operate correctly. We're saying that it's minus 104 dBm, which is a fairly weak signal. Okay, so if we recall Fritz's equation, right, what are the sort of things that we have? Now, looking at this drawing that we have here, you can see that we have a transmit antenna, we have a receive antenna, and we have a certain distance. Okay, so what we are going to do is we are going to figure out how much transmit power we need. Now, our first equation was set for power received, but if you look closely, we know how to we know the transmit gain, right? We know how much the transmit gain is. We know how much the receive antenna gain is. Well, we don't really know free space loss, but we know R. And from R, we can calculate the free space loss. They actually told us what the receive power is, right? That's at minus 104 dBm. So what we need to calculate is the transmit power. So let's go ahead and do that. Okay. Oops. So first we need to rearrange our equation. So that's what we did. We're going to do here. So notice that now we made our equation in terms of uh, the received power and the gains and the free space loss. So now we calculate how much transmit power we need. So if you go back to lecture one, we had an expression for free space loss, right? 20 log of the distance plus 20 log of the frequency, which in our case is the 1800 megahertz, minus 147.55. You plug in all your numbers and you get that the free space loss is 97.6 dB. Putting it all into the equation, right? Putting it all into equation, let's call this over here equation number one. Putting it all into equation number one, you will see that you need a transmit antenna, the power going into the antenna, I should say, is minus 14.4 dBm. So if you, in this problem, if we were to put minus 14.4 dBm into our antenna, you would receive minus 104 at 1,000 meters away as the input to the receiver on the mobile unit. Okay. So a practical measure of signal strength views a signal waveform, and we're going to use the GFT quite a bit in our lecture. So just be paying attention. Almost everything in our textbook, they call it GFT. But this is a time-varying waveform applied across a 1 ohm resistor. Just think about it like that. And that's without any loss of generality, right? So if you have what that means, if you have a different resistance than 1 ohm, you would plug that in. But for ease of discussion and again, without any loss of generality, we just assume 1 ohm, okay? So let's talk about energy. How much energy does GFT have? Well, if you remember back to some of your basic circuit courses, you might remember that they tell you that the energy in a signal is nothing but the integral of the square of the signal, okay? The square of the signal. So, and that would be for a signal that is real. I mean, and by real, we mean that it has no imaginary part, okay? Again, going back to some of your initial circuits, um, and even back to mathematics when they were talking about complex numbers, right? A real number is a number that has no imaginary part. But sometimes we do uh, deal with complex valued signals, and in such a case, all right, the what we do in a complex valued signal is we take the magnitude, right? So if you remember the magnitude of a number, we use the two bars to represent the magnitude. And if um, well, let's not call it A, let's call it X. Let's say X equals A plus JB. You might remember that the magnitude of X equals the square root of A squared plus B squared. Okay? The same thing. That's the magnitude that we're talking about in this integral. So, what happened? I think I skipped a slide. No, we're good. Okay, if in an infinite class of signals, right? Uh, or an entire class of signals, excuse me, you have an infinite energy, then energy is no longer important or meaningful as it relates to relative sizes. That's why we have the two, right? That's why we use both energy and power, because if a signal goes on forever, for example, it will have infinite power. So if I turn on a signal source and I let it run forever, that means in order for me to keep the signal going, I need infinite energy. So that is not a good measure, for example, in such an example. So when you have a signal whose amplitude does not, and let me say does not go to zero. So whenever you see me use the arrow is something that not go to or tend to, right? As t goes to infinity, so if the signal doesn't tend to go to zero, it means that the energy must be infinite from my prior example that I was talking about. In those cases, it's always much more meaningful and it makes sense to talk about average signal power. And that's what we talk about. P of G is the average signal power. And that is given by 1 over t, where t would be an interval of time that you define. And if your signal is periodic, normally we use a period of the signal. But not all power signals, as we're going to call them, uh, have a, or have to be periodic, right? They just have to go on forever, if you will, for a very, very long time. Here are two examples. So the first signal, notice that after it goes through a certain peak, right? It goes through a certain peak, you can see the signal diminishes, diminishes, and continues to diminish to a point that if we let time continue to run after this point here, you would see that the signal eventually will reach zero, right? So think of this as some kind of circuit. There was some capacitor or something. Initially, you got a charge, you remove the DC source or whatever source, and it begins to discharge. And eventually, it will go to zero unless you apply more energy to it, right? The second signal, B here, while it goes on forever, you can't say where it's going to stop, right? And we only look at a certain period or point in time. You can see the signal is not periodic, but it does not tend to zero. So this signal does not tend to zero. Okay, that's signal in B. Okay, you can see the signal will go on forever. This we will characterize more as it with its average power than we would as using its energy. So what would be the suitable? Here's example number two, and what we're looking is what would be a good measure for the two signals, right? So in part A, since we notice by inspection that the signal goes to zero, right? Notice again, this signal in part A is going down to zero, right? So the signal does tend to go to zero as t moves towards infinity, then the correct measure to use will be energy. Now, we just have to integrate this signal, and I trust that you guys can do this integral, right? Notice that the signal has sort of two parts to it. The first part is sort of constant, so between -1 and 0, okay, between -1 and 0, You notice that the signal is constant with an amplitude of 2. So that magnitude is 2, so 2 squared, that's your GT between -1 and 0. And this is a typo. I apologize for that. It should have been from 0 to infinity, right? But we really are not going to go 0 to infinity. Be Oh yes, we are going to go 0 to infinity. Excuse me, pardon me. And then if you evaluate this integral, you end up at 4 plus 4 and equals 8. So your energy has 8. And if we're measuring this in MKS unit, that will be 8 joules. Okay. And the second one, since as t does not tend to 0 as t goes to infinity, right? Does not, we will use power. And again, you have to define some kind of a period. And we have, or time interval, but we happen to notice that the signal MB is periodic, so we can just integrate over one period. And notice that from here to here, right, from here to here, is one period, so between -1 and 1. So that's what we're going to integrate. And notice that if we were to define the period, t would equal from 1 to -1. So what is t? 1 minus -1 equals 2. That's where this 2 comes from. Okay? So simple integration, and we end up with having a power of 1/3. And again, in MKS units, that would have been watts, or 1/3 watt. Um, a couple of more examples. So here's example number 3. We want to determine the power and the RMS values. These are all um, periodic signals, so that's why we're just going to go ahead and calculate the, the power and RMS value. So for the first equation, and let me remind you, that's just c cosine of omega 0 t plus a phase theta. Um, and you just square the signal, and then you have to remember the identities for cosine square is 1 plus 2 times the argument, right? So if I go cosine of x squared, right, that would be 1 plus cosine of 2x, right? It's the same. So that's what this integral is been done over. And remember, we have to do the limit as t tends to infinity. And you run through the equation, and pretty soon you end up realizing that this all comes down to, and if you run through the equations and complete the integral, or the integration, you end up with c squared over 2, which is the power. Now, the RMS value for us is nothing but the square root of the power. And that goes back to the fact that we said initially that we are going to normalize everything to 1 ohm. So it makes it easier for us. This is one of the advantage of doing that. So it's the power of the signal, and RMS is just the square root of the power, which ends up being c over square root of 2. And again, you should be able to convince yourself of that. The same thing for the other two signals. It turns out if this is a linear process of just adding two signals, so it should come as no surprise to you guys that you end up with a power over here that is actually adding the power of two individual signals, right? It's a linear process. And then the RMS value is nothing but the square root of the power. Uh, Now, we can extend this to any sum of sinusoids. So if I had any sinusoids, I can easily just calculate what the C values are, square those, and then add them up all together, which is what this formula is saying. And then you put 1/2 of that, and there you go. You have the result for the power of n, any number of sinusoids that you would need to add together. And this is true as long as Wn, or the omega values. And remember, omega here, right? That's the radial frequency. So omega is always equal to 2 pi of the frequency, of the linear frequency, okay? So this is in hertz, and this is in radians per second, okay? Now for the exponential, again, if you run down through the integral and do the limit, you end up with noting, you have to note that the magnitude of ej to the omega 0t equals 1. Therefore, this value, when I square it, still equals 1. So I'm left with a constant, which means that the power is nothing but t0, d squared, I'm sorry, um, which is the final result here, right? And we put it as an absolute value under the, just to stay general in nature in case d is a complex number. All right, some closing comments on signal strengths. Observe that the signal power is the time average or the mean of the signal amplitude squared, okay? The square root of PJ is the familiar, or the power of the signal is the familiar RMS value. Um, During transmission over a channel, the message signals are corrupted by unwanted signals or noise, so please remember that. So if you were trying to measure the power in the lab, in theory, right, you always are going to have some noise, so be careful with that. When we're judging the power of us of the signal, and you're trying to do this integral, normally we don't worry about the noise. The quality of the receiving signal is judged by the relative sizes, right? Remember the whole thing about that we were talking about relative sizes, is because when we measure signal to noise ratio, you guys remember that as NR, right? Which is nothing but the power of the signal. In this case, we're calling it power G. So it's whatever noise value you have. So this is the relative. This is when we say relative signal sizes of the signals. It's because it's the power of the signal over the power of the noise. Okay. The power ratio between the message signal and the noise is what's important, in other words. And it's as it says on this slide, it's a strong indication of the received signal quality. Okay, so enough about signal strengths. Let's talk a little bit about signal classification. And signals can be classified in so many different ways, right? So, and here's several pairs of classes of signals that we will study in class either pretty soon or sometime in the future, right? So we talk about continuous time and discrete time signals. We talk about analog and digital signals. We will talk about periodic and aperiodic signals. Fully by this point, everybody understands what a periodic or aperiodic signal, right? And if not, we'll do a quick little talk about it. Energy and power signals, we just talked about this. And then deterministic or random signals, we'll also talk about that. So a signal that has a value at every time t is considered a continuous signal. But the most popular one is a sinusoid, right? Notice that a sinusoid, if I draw a sinusoid here, and I say that this is, right, this is, let's say, voltage, and this is time, these axes, right? This signal exists forever, right? It goes on forever, and any point in time that you want to take a measure, you have a value. So it's a continuous signal, it exists forever. Now, a discrete signal only exists at certain n values, and here is an integer times t, where t is some interval that we define, right? This t is not associated with the period of the signal. It's more associated with the sampling time. How often am I going to look at the signal? And I'm going to look at the signal at uh, uh, the same increment in time. So if I'm looking at my little sinusoid here, I might take a sample at 0. Let's say I take a sample at 1. I'm trying to draw a little circle here. Another sample here, another sample here. So when I end up looking at the signal, or at my discrete signal, what I have is a series of, right, of dots, let's say dots for now. And that's what your discrete signal looks like. You do not have values in between. So if my sampling time is 1 second, I know my signal at 0, I know my signal at 1 and at 2. What happens in between, I don't keep that information, right? I can probably make inferences as to what the values are, right? But I don't keep those values. Um, a signal that is continuous in time, we normally call those analog signals. And a signal that exists only at finite number of time values or has a finite number of values, that's what we call a digital signal. Okay. Um, the two concepts of analog signal and continuous signals are not the same. The same thing is true for discrete time and digital signals. Okay. An analog signal amplitude can take on an infinite number. It can be anything inside its continuum, right? My example of the sinusoid continuous signal, it can go between +1 and -1, and depending on where you decide to go to make a measurement or look at it, if you will, that's the value that you get. But immediately it's constantly changing, right? A binary signal is a digital signal. So in order to qualify as a digital signal, right? Remember that you are restricted to two numbers. That's what a binary means. It's 1 or 0 or 1, right? Okay, continuing with this sort of talk about signals, we also like to talk about signals beyond just the ones that take on the two levels, right? We actually like to talk about M values, and you'll hear me throughout the course uh, frequently talking about these M-ary signals. An M-ary signal is a signal that can take on more two levels or more, right? But it's this M discrete levels, right? So an M-ary signal uh, the binary is a special case. Notice that we call it binary. It's a special case in M-ary signals where M equals 2. Okay. Um, so we have a few examples here. Here's an A is our continuous signal. Uh, B is a digital and continuous time signal. And then if you want to talk about an analog discrete signal, see, this is the one where we took the samples of from this signal, okay? And these are the samples. So notice how we look at it at discrete intervals of time. And then the final signal and D here is a discrete digital signal. In our case, this is a binary signal, right? It can take only one of two values, right? And we did talk about signals with different levels, and we talked about how uh, if you have 16 levels of the sort and how to calculate how many bits that takes and stuff. We did that in lecture 1. This is going to come up over and over in the course, periodic signals. At many times, we just look at one period of the signal because we know that it's just going to repeat, okay? So I want to draw your guys' attention to a periodic signal definition, okay? So a signal is periodic if at at some future time t0, the signal repeats, all right? Or it was equal to itself at the at any increments of t0. It's always going to be the same. That's the definition of periodicity, right? A signal is aperiodic or non-periodic, some people sometimes call it, if there's no value of t that satisfies the above condition. Okay. Um, Another way of looking at a periodic signal is that it remains unchanged when shift by one period. So if you define a period to zero and you shift time by that period, you should have the same signal again, right? That's a definition of periodic signal as well, or is a characteristic of periodic signals, right? Which is what our example is showing you here in this figure. So we define T0, right? And notice that if I look at this signal T0 seconds again, from here to here, you have T0. Notice that you get the same signal again, the same values and everything. That's a periodic signal, right? And we will be doing that throughout the course several times, different places. Um, Getting back to this energy and power of signal. So a signal with finite energy is an energy signal, and a signal with finite power is a power signal. Now, we have we have to realize that things need to stay bounded for us so that we can deal with it, right? In our line of work, if you will, we really don't like to deal with infinity, right? So for a signal, GT that is an energy signal, it has to be bounded. That means that the energy, right? This is the formula for energy, this integral, right? It has to be bounded, meaning that it has to be less than infinity to qualify for an energy signal. So not only does it have to tend to zero, as we said before, right? But whatever it is, the energy cannot go to infinity, right? If it goes to infinity, we really don't know what to do with that, okay? Um, the same thing happens with a finite and non-zero power or mean square value, which is kind of the same thing. One is the square of the other. You want to make sure that your power is also bounded. So power should be greater than zero, right? Or the definition of power is this limit of this integral, or less than infinity, right? If you have a signal that does not, that you think is a power signal, but it violates any of those two conditions, then it is not a power signal. Because again, we don't know how to deal with something that would be less than zero power. Such a thing doesn't exist actually. And if the power tends to go to infinity, again, we don't know how to deal with that. We don't. Okay. Um, so two examples here of signals and this figure 2.2. Observe that the power is, again, is a time average of the energy, right? That's the definition of power anyway. Since we're averaging, what do I want to say this? A signal with finite energy has zero power, right? So the thing about power is you keep feeding energy so that the signal keeps going. So you have a certain energy per time, right? In this case, there was some energy injected into the system, and then it was led to it did whatever function we wanted it to, and then it's going to go to zero. In this case of this ramp, so we ramp the signal, and then the signal drops again, and then something has to increase it. Let's think about it that way, right? So in order for our signal not to die out, we have to constantly be feeding it energy over time, which is the definition of power, okay? Now, there are certain signals that are neither energy nor are they power signal. One such signal is the ramp, right? So what is a ramp? A ramp signal is nothing but something that goes up, up. Let's say if A is positive in this expression, GT over a ramp, the function is G of T equals A times T. See, for this signal to keep going up, 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 and up, you have to continuously be feeding it energy. And as time goes on, you have to feed even more energy and more. And where does it stop? You don't know. So this signal is not a realistic signal. Um, in the long term, if you will, right? In the long term, we just can't feed it infinite energy. Okay, another classification of signal that we mentioned earlier were deterministic and random signals, right? So a deterministic signal is a signal that um, pretty much you have a mathematical or graphical form, right? So you don't kind of know what the signal is going to look like. You have an expression such as these two. Figure 2.2, those two signals are deterministic because I can come up with a mathematical expression for it. However, if a signal, the only way you can describe it is through some probability of a value of the signal rather than a full deterministic mathematical graphical description, that's what we call a random signal. It so happens that noise is a random signal, right? We kind of mentioned that before. And that's true for most noise sources that we encounter in the real world. They're sort of random in nature, and we define them with probabilities. What's the probability of the signal, right? There's a certain uh, randomness about the signal. It turns out, and it's kind of a funny thing, noise is random, but so is information, right? If I can sit down and put something in a graphical form, or more generally, perhaps in mathematical form, there's no information at that point, right? This is why the carrier, right? When we talked about modulation earlier, this is why the carrier itself has no information, right? It's a deterministic signal. I know exactly what it is. The message, on the other hand, I really don't know what it is. If I knew what it is, it stops being a message, right? It stops containing information for me. So it's um, kind of a hard concept to grasp at the beginning, but information is random in nature, and we actually exploit that in communication. That's not going to be part of our course, but that is something that gets exploited when it comes to communications. Okay. All right. So let's go ahead and talk about signal operations. There's all kinds of signal operations. We're going to focus on three of them, right? So let's focus and discuss um, what do we mean by time shifting. Notice we're focusing on time, right? We're going to talk about time scaling and then time inversion. Okay. Um, so let's consider a signal like in this figure, 2.6 from our textbook. Um, and let's say I want to delay the signal, right, by t seconds, right? I want to just delay the signal. How do I represent that in mathematical forms? How do I represent my signal so I can do operations on it, for example? So let's say I have a phi signal, okay? And if one way I can, let's say phi signal is my delayed signal. I should mention that. So in other words, if I look at phi at t plus tau, it should equal g of t, right? Which is my original signal. And you can see that, right? I take my signal g of t, I delay it, and then um, if I delay it, I'm actually just looking at g of t happening a little bit later, right? And there's two ways to do it. You can look at it as adding the delay to phi of t or subtracting the delay of g of t. Both operations are one and the same. Okay. Um, so we normally use the second one. We normally use this one, right, for mathematical purposes. Okay. Um, and let me see. Oh, yeah. So I was talking about we normally look at this one for mathematical purposes. So normally you would see some expression that looks like this: phi of t equals g t minus tau. Okay. Um, if t is positive, right, in that expression, remember the minus is part of the expression. So if t is positive, right, it means that we time shift to the right or delay the signal, right? Now, if t is positive, right, again, remember what the equation we're looking at is this equation here, right? If t is negative, on the other hand, then we say that it advances, which is this case. That's why we're showing g of t plus capital T, right? So it advances. It means it happens before our g of t, okay? Remember, positive. Remember, the equation is g of t minus capital T. This is, okay, this is a delay. If you have g, and this t is positive, right? If you have g of t minus capital T, for just to express t as capital T as a negative number, this is the same as g of t plus capital T, right? And this is an advance, okay? Time scaling. Time scaling is one of those interesting things that we can do to signals. I always find it sort of sort of a fun thing. Um, so let's say that my original signal looks something like this. Let's say that I want to compress my signal by a factor of 2. Well, in order to compress the signal, and let's call it the signal is phi of t, then what I do is I say phi of t, and then I take all the t's and I multiply it by whatever that number of compression I want, which in my case is 2, right? Um, the textbook likes always to talk about these in terms of phi. It's the same sort of terminology, right? It's like saying that, oh, now whenever I evaluate g for t, I evaluate phi for t over 2, right? The more common nomenclature that we use is we say phi of t equals g of t over 2, okay? Um, the same thing happens when I want to expand my signal. Okay, so if I want to expand the signal, okay, um, what I do is I divide by whatever number I want to uh, expand the signal. So in that case, when I want to expand, right, if I have phi of t, I would say that is good. And again, I want to say the same. I want to expand it by a factor of 2. I say g of t over 2. Okay. Um, So to sort of summarize this time scaling, let's do it in more general terms. So let's talk about a scaling factor. So we're going to talk about um, phi of t as being a function of g of a, a of t, where that a is going to be my factor, right? So if a is greater than 1, right, then we say that we're going to compress the signal. If A is, and then, where did it go? Okay. Um, to expand this, slow down in time by a factor of A greater. Okay, so it's expanded, okay, if A is greater than 1, but now we're going to divide by A, okay? So, in summary, if you look at it, if the factor that you are using is greater than 1, right? That's just straight A. And when we talk about here, the factor is less than 1, we're actually talking about 1 minus 1 over A, right? So the slide kind of has a weird way of saying it, but I would have preferred not to use this expression here, right? And Just let it all be generic in this term, right? So just define it as GAT, and then um, you can keep it generic that way. Um, so here's an example again from the textbook, right? And what the textbook wants to do is, or wants you to do is, for A, sketch 3t of G, where this is your G of t. So we know that if you do 3t, the easiest way to kind of do that is uh, to say that um, your old your t equals, right, 3t new, right? So I'm doing exercise or part A, right? And we're really interested in knowing what t new is. So t new is actually your t divided by 3, right? So if I take t, uh, sorry, so if I take t and t new and make a really quick little table here, okay? So what points do we know? We know 6, 12, 15, and 24. Well, 6, 12, 15, and 24, right? And t new is always divided by 3. So this will be a 2, right? This will be a 4. This will be a 5. And I keep looking at the graph for the numbers, sorry, 8. So now you'll see that 6, right? 6 becomes 2. The 12 becomes 4, which is here, where it crosses 0. 15, right? 15 becomes 5 when I look at my table, so you have 15 right there. And then the 24 becomes 8. And that's how you compress the signal. Um, I find that it's easier if I do this thing where I say t equals t new, uh, or a times t new, and a here is 3. Watch when you, so that's when we compress. Watch when you expand. The same thing sort of is kind of helpful for you. So for B, hopefully my handwriting is kind of makes sense to you guys. The same thing, I'm going to say that t equals t new over 2. So that means that t new equals 2t. Right, and again, let's make a little table here if I can keep it straight. So here is t and here's t new, right? What numbers do we know on the x and the t-axis, which is the horizontal axis? I know of -3, I know of -1, and I know 1, right? Those are the values that you see here, okay? So this will be -6, this will be -2, and this one will be 2. And then that's exactly what happened, right? Here's the -6, so the -3 becomes -6, the -1 becomes -2, and the 1 becomes 2 right over here. And that's how you can see how it expands, right? So it's easy to do these sketches of expansion and compression. Again, like I said, I like to do the little table. It helps me a lot. And normally for these kind of exercises and stuff like that, it's kind of easy to look at it in this way. So I can actually give you the two uh, graphs, and you can immediately almost tell me what the value of A is, right? So by just taking a few yeah, I will call them samples, and kind of easily determine what A is as well. Um, Time inversion, you can call it flipping the signal, right? We're going to flip the signal. And then you know that we can flip it in uh, both around the T or the Y axis here, right? But time inversion, we're going to flip it around sort of the vertical axis here, which most cases we call it the Y axis, right? So, and the operation really is um, your new phi of t equals g of minus t, right? Notice the minus. It's just a minus um, to invert the signal. And notice what it does to the signal. Right here's your g of t. Notice how you have like a straight line on the positive side and what seems to look like an exponential right here. Well, when you flip it around the vertical axis here, then you have the straight side on this way, but kind of instead of going left to right, declining from left to right now is increasing. And the same sort of thing with the this curved shape, right? Now it's just curving to the other side. Notice that you could have mirrored or imaged the signal around the t-axis, but that's actually, when you do that, you actually, your phi of t, okay, your phi, oops, sorry, it's kind of too low on the graph, so it's a little hard for me to do. So your phi of t will equal minus g of t. Notice that it's the whole function that gets negated, not the t value, but the whole function. And that flips it around the horizontal axis. Okay, so here's another example of time inversion. So your original g of t, right? We said that um, you do g of t, right, is this function here. And in order for me to get the inverted function, if I want to call it, right, if I want to call it phi of t, all I have to do is do g of minus t. Well, g of t, right, is e to the t1 half. But now, in order to find out phi of t, or the inverted signal, I'm going to take the e, and I'm going to make t negative. So that's minus t and over 2. And then when you draw it, you should get this. And you should get this shape. Okay? Here's a very special function. When I have a couple of these in the class. And the first one that we're going to talk about is the unit impulse signal, which is a very curious signal with a lot of really good mathematical uses in communications, right? Um, it was first proposed or defined by Mr. Dirac. That's why sometimes it is also called the Dirac delta function. And it's quite interesting, right? So this function, which we use the Greek letter delta, right? Um, I think this is lowercase delta. Uh, somebody might correct me if I have it wrong. I might have my Greek alphabet wrong, so I apologize for that. But I think that's what it's called. Um, Equals 0 for all t's except for t equals 0. And it says nothing about what happens at t equals 0, does it? It's just saying that except for t equals 0, this function is 0. But there's another thing that defines this function, and it's this integral right here. Okay, this integral. Minus infinity to infinity, delta t has to equal 1. Now, normally we draw this, or we sketch this signal as you see here. Nothing but an arrow at 0, right? Now, and it's infinitely thin. It's like a line going up to infinity. Well, but wait a second. Doesn't the integral, right, define the area under the curve? Well, if it does, that's kind of a weird thing, isn't it? And it is. It truly is. It's a weird thing. But the real way to think about this is that you have some very thin um sort of rectangle and with epsilon, right? So, and the height of this is 1 over epsilon. So you can imagine if epsilon is a really low number, let's say for argument's sake that epsilon, and we're calling a really low number, we're saying epsilon is 0.001. Let's say that's a really small number, which by all practical purposes, not really a really small number, but let's say. So if I go ahead and do that, you can see this is the width of this pulse, right? Because notice it goes from minus half epsilon to plus half epsilon. But the height is 1 over epsilon. So the 1 over epsilon, right, equals 1,000. So it's only 0.001 wide, but its height, oops, I'm missing a zero, is 1,000. Okay, that's the kind of way that you can think about it. So this is what we're showing here in B is really more like an approximation. It kind of helps us think about what this function kind of is, right? Um, but it has a lot of interesting properties that we're going to continue to look at. Now, let's say that I have any function that I want, and I'm going to multiply it by the impulse, right? You have to remember that the impulse is zero everywhere else except for zero. So if I'm multiplying a function phi by the impulse function, right, I really don't care about this function phi, anywhere else but at zero, right? Because I know that this multiplication outside of t equals zero, right? This function anywhere outside of t equals zero is going to be zero, right? That's the impulse function. And as such, right, I only care when phi equals zero, okay? Because everywhere else, this multiplication is going to be zero, right? Now, we learned a little while ago about delaying a signal. So if you delay the impulse signal, right, and you multiply it by a function or a signal phi of t, again, you're only interested, right, at where this function is not zero, which in our case, because we delayed that impulse to capital T seconds, now we're only interested in the function evaluated at t equals capital T. Okay, kind of an interesting result, right? Um, so that leads us to what's known as the sampling property of the unit impulse function, right? So the general rule for this is we're going to use the multiplication property of the impulse function. If we use that in this integral, right, we end up with something really, really interesting. So if I want to evaluate this integral, first of all, this portion, the function, right? Remember, I only care about the function, what happens at value t. As soon as I do that, as soon as I evaluate this function at capital T, it becomes a constant and I can take it outside of the integral. Now, if I look at the integral now, I'm only integrating over the impulse function. And what did we say that the integral of the input function was, right? If you remember the definition, we said that it would equal 1, right? So going back to the slide, if the integral equals 1, this whole integral, which didn't look so nice at the beginning, actually ends up being a constant, which is the function that was multiplying the impulse evaluated at capital T. Okay? We call this the sampling, or if you want to call it the shifting, but most people, we more commonly, we call it the sampling property of the unit impulse function, right? And you can see a much clearer uh, expression or definition for this property down here, right? So if I integrate from A to B, um, and it doesn't matter what the value of t is, as long as the limits of the integration, okay, are within, t is within, right? T, the value of t is within the limits of integration, you evaluate phi of t. If it's not, it's equal to 0, right? So if t is outside of a and b, it just goes straight to 0. Another interesting function is the unit step function. And believe it or not, this function is in our lives and in a laboratory everywhere we go, right? The the unit step function says that at time equals 0 and forward, right? This function equals 1, okay? Equals 1. And anything less than 0, it equals 0, right? And this is what that function looks like, right? Before t equals 0, it's 0. Right at 0, it becomes 1, right? If you think about this just a little bit, that's the same thing we do when we throw a switch. So before, let's say, or we connect the battery to our circuit, before we switch, everything was 0. You turn on the switch, and everything all of a sudden becomes biased or has a voltage applied to it, right? Let's say we were able to do that instantaneously. That's what U of t is, right? And for example, if here's an example, this exponential function, okay, oops, this exponential function would have continued, if I can draw it properly, right? Would have continued from the negative side. No, that's not the right way to draw that, but hopefully you guys kind of get the idea. Let me see if I can. I don't think my drawing skills are up to par today, um, but hopefully you guys get the idea, right? This would have kept on going, whatever, right? But once I multiply it by u of t, anything that was on the 0 side, um, anything that was on the 0 side, on this side, right? Anything over here goes away, and I end up with what was shown in the graph originally. And let me erase my red line so that hopefully you guys can still see that. Okay. Now, there is a relationship between the unit step, right, function and our direct delta or Dirac delta function, right? Um, if you remember, you can integrate anywhere from minus infinity. If you think about it, right? You can integrate anywhere from minus infinity to a value t of the direct function, and it will equal 1 for t greater than 0 and 0 for t less than 0. But wait a second, didn't we just say that this, right, this whole thing was the unit step function? And that's exactly right. So the integral of the unit impulse function equals the unit step function. Isn't that an interesting result, right? Which also we can prove, all right? We could prove that the derivative of the unit step function equals the Dirac function, okay? Um, so I have a quick octave exercise that I would like to do for you guys to show you how we create this signal using the unit step function, and just a little bit of an exercise that we want to do. And what we're trying to do is we're trying to recreate this expression, which says y of t equals the exponent of minus t times sine 6 pi t u of t plus 1. Okay? And we wish to create this. Okay. So we're going to go ahead and evaluate that function using octave, as I'm showing here. Notice that first I just define what my times are going to be. So I'm going to go from -2 to 3 in zero point 0.01 steps. So that's how the points that I'm going to use to evaluate my function. And those are my time points. Uh, the actual function that was on the slide is actually on line 10, but I'm going to break, because it has 3 parts, let's break them down and see what each part kind of does. All right, so I'm going to start with the sinusoid. which is no surprise if you run this, right? And for those of you taking the class, this has already been uploaded to Canvas. Um, and it is called Chapter 2, Exercise 1, SIGGRAPH.m. And you get a sinusoid. Nothing impressive, nothing to write home about, but that's what you get, right? And I sometimes like to break these things down because it kind of helps me understand what the steps are, and I'm hoping that this helps you guys. Now, the next step that I'm going to do, okay, is I am now going to take my sinusoid that I created, and I'm going to multiply it by a time advanced unit step. Notice how I say t plus 1, okay? Here's t plus 1, and this function is actually a function that I created, and as long as you put in the same directory as the function, and that's your active directory, it'll find it, right? Both tools will find either Octave or MATLAB. And then here's what unit step is, and honestly, guys, it couldn't be been any easier. So the function is called uStep for unit step, and it's just a Boolean evaluation, or Boolean evaluation, I should say. So as long as t is greater or equal to 0, right, this Boolean is true, which evaluates to 1. If it's less than 0, well, it's false, which evaluates to 0. And there you go. That's your unit step, right? And in our case, we are advancing it, so it won't start at 0. It should start, if I'm advancing it by 1, it should start at -1. So my sinusoid should be, for lack of a better word, it will be chopped at -1, and it'll be 0 between -2 and -1, and then a sinusoid from there on, right? Because I'm just multiplying it by 1 after that. So let's go ahead and run that. And pretty much that's what it does. See, this is the unit step in action, right? If I plotted the unit step, you would see you have 0, and then it goes up to 1. And when you multiply that by the sinusoid that we had before, this is the result. Now, the full function actually multiplies then by the exponential of minus t. Now, the exponential, because it's minus t, should be a decreasing exponential. Oops, I activated the wrong line. I meant to activate this one. So now in line number 10, you have the full expression with the 3 terms in it, known as the exponential of minus t. So now what I expect is the unit step function, which is what I'm looking at right now, multiplied by the sinusoid, and an exponential multiplied by that. And now the exponential actually drops, right? And if you ever have plotted an exponential, you know that at t equals 0, right, this should be equal to 1, okay? So let's see what we get. And sure enough, right, notice that at -1, the amplitude of the signal goes much higher. Why is that? Because e of -1, right, when t is -1, okay, is a large number, right? -1 does, so that'll be e, which has a value of 2.718, right? That's what this value is. Yeah, 2.718. But that's kind of what this amplitude at the beginning goes to, and then in typical exponential fashion, drops from there, right? As an exponential, okay? And that's about it. And if you remember what modulation is, you can think about this as a modulated signal. It's being modulated by an exponential. Hmm? Not a real useful and realistic signal in the real world, but kind of what you can think about. So now let's return to the slide. Okay, so signals and vectors. Um, this concept of vectors, and you probably remember it from both your mathematics and maybe your physics class. We talk about vectors, and maybe in some of your circuit analysis classes, they might have mentioned vectors when they talked about phasors and that sort of thing. Um, so a vector normally, the minimum requirements for vectors is we need at least 2 points, right? Or the starting point and the magnitude and angle, right? In all honesty, you need at least 2 points for a vector, right? Now, consider that I wanted to have something that has a finite number of n time instances, right? We can actually write that as a vector, right? Because again, what is a vector but a collection of points, right? If you think about that long enough, you'll find that. So let's say that I have a signal g of t, and I have a closed interval in time. So whenever you see me talk about an interval in time, right, and most textbooks, or I shouldn't say most textbooks, but textbooks have a tendency to use this sort of nomenclature. So this says from A to B. That's what this is, right? It's pronounced from A to B. So if I pick n uniform points in an interval A to B, I'll have a point at T1 that we call A, at T2 with A plus epsilon. I could have written delta, right? Or T3A plus 2 epsilon, so on and so forth, up to T of n, where you have A plus n minus 1 epsilon, which will equal to B. What is the value of epsilon? Well, if I know how many points I want, epsilon evaluates to B minus A over n minus 1, right? And believe it or not, we've been doing this all along. Remember that T value that I just showed you guys that I kind of brushed over when I was talking about in octave? That's nothing but something like this, right? Right? It's a vector of the values of time that I'm interested in. I then take those values of time and I evaluate my function, and my function actually is a vector. So that function that I was evaluating and that I was plotting is nothing but the concept of a vector, noticed programmatically in octave. Okay? So as the number of n increases, the sampled signal, that's what we're calling it. So when I said that I was going between -2 to +3 and zero point zero 0.01 intervals, at zero point zero 0.01 intervals, that's my epsilon, okay? Um, the smaller I make it, that means the more samples I have, or n increases, right? The size of my vector becomes bigger. Nothing to write home about, right? It just grows in size. So eventually, n, as n goes to infinity, right? Um, you have a really long dimension. And what happens when you do that is epsilon tends to zero as n increases, and the signal vector g would actually transform itself into g of t. So in other words, right? In other words, as we can talk about the limit as n goes to infinity of g, of vector g. That's why this is bolded. We talk about vectors. The textbook does this. Talks about vectors as bolded letters, right? As the vector g grows in size as n goes to infinity, you then get your signal g of t back within the interval that you evaluated it at. So this letter here is not epsilon. It says t belongs to the interval between a and b. Okay. Um, it seems new, right? The whole vector thing, but I already spoke about this. This is not new, right? So here's a quick little snippet of the way we could use this, right? Actually, why don't we go ahead and transfer real quick to octave, and why don't we try this, right? Let's go ahead and try this. Okay, so here we are in octave. What I'm going to do is I'm going to start a new um, M file, and for lack of a better name, I'm just going to call it. It's a new script. Let's call it. What should we call it? Well, I don't have the file. New script. Right. let's call it, we'll name it in a second. I'm drawing a blank for a name. Let's try to do the same thing that we were doing on the screen. So from 0 to pi divided by 2, and then we're going to evaluate it at the 2 times pi or 2 pi, right? Um, so if I run the script real quick, you'll notice, oh, there you go. Now it's asking me to save it. So let's call it chapter 2. Oh, I don't, um, let's call it vector example. Okay, that's good enough. Save. All right, so if I run this real quick and I go look at the command window, you'll see you just get a whole bunch of values. If you want to see them sort of in a column, I put uh, a single quote at the end, and that's going to transpose it. Again, if we run this real quick, you'll see now they're in column form, right? That, again, nothing really huge or important to write about. Now let's say that our function g, oops, sorry, I meant to put the semicolon. Let's say that my vector g, I should call it, equals sine of t, right? And that's just those values from 0 to 2 pi and pi over 2 increments, right? This time, let me go ahead and just plot t comma g, okay? Why don't we just uh, print that on the command window. So we go to the command window, that's pretty much what's on the slide, right? So we evaluate it at 0, at pi over 2. If you evaluate sine at pi over 2, you should get 1, then 0, then -1, then 0 again. Okay. Again, nothing huge to write about, but let's play with this increment thing, right? Because we're talking as it goes to infinity, right? Um, if you look closely right now, we only have 5 values, right? So n equals 5. Actually, why don't we go ahead and plot? Let's look at it in a graph. Plot, um, what is it? T comma G, real simple plot with nothing fancy. We don't have to get too fancy with it. Let's go ahead and run that. And something happened. Where did the graph window go? Something tells me that my computer's hiding the graph window from us. There it is. Okay. Notice that because I only have 5 points and we were expecting this to be a sinusoidal, we didn't get a sinusoidal. Or did we? Right? I have only 5 points. 1, 2. There's one that goes through 0. Actually, let's just go ahead and turn the grid on. So that we kind of see a grid. It's kind of nice to see that. See, there's a point here at pi that goes through 0, then -1, and back to 0. Okay, so is that a sinusoid? Well, why don't we increase n by a factor, let's say of 10, right? So instead of dividing by pi over 2, let's divide it by pi over 20. So we should get a lot more points now, right? So and sure enough, we did get a lot of more points, and now it does look like a sinusoid, right? In fact, why don't we, instead of going to such a large number, instead of increasing it by 10, let's just increase it by an order of 2. So instead of pi over 2, let's do pi over 4. See, had I done that before, you see the points begin to uh, as we increase, now the function looks more like a sinusoid. That's what it meant when you do the limit as n goes to infinity, right? And then you can see if I go another factor of 2, I go to pi over 8, now it really begins to look like a sinusoid. And then if I go to the pi over 20, like I did a little while ago, at this point, it's really hard to not tell it's a sinusoid. Okay, if you look really closely, you might be able to see it. But if I definitely go to a factor of, well, dividing by 100, you just, at that point, you really can't see it. Okay. If you ever want to know, right, you can always look here in the workspace, and you can always see how much more points you have as you keep changing the value of your increment and that sort of thing, right? So Right now, n equals 201. Okay, and you can see you get a graph that you really can't distinguish from a sinusoid anymore. Okay, so that's what it means when we say the limit of n goes to infinity. We have another exercise. So another octave exercise. Let's say we want to take this function, which is the exponential uh, minus the absolute value of t over 4, and then we are going to subtract u of t minus u of t minus 4. Notice that when you do u of t minus u of t minus 4, I wonder what we get. Why don't we go ahead and go do some of this in an octave. I also wanted, we're also going to be taking, um, doing some uh, expansion by doing y of 2t and then y of delay. No, this is an advance y of t plus 2, right? And you can see those graphs are here on this slide. And then the same thing with y3 of 2 minus 2t, right? So this one inverts the signal and also time shifts the signal. That's what y of 3 does, okay? Um, and this is actually from section 2.10 of the textbook, which it does a few of these exercises. I'm going to do the first part. I want to show you guys what u of t minus u of t minus 4 does. And you can start by sketching that first by hand. See if you can do it by hand, and then see if you get the same result in Octave. So let me go to Octave real quick. Here's Octave. Um, Let me see. I want to open. This is chapter 2, exercise 2.6. I believe it's this one. Um, Let me double check from minus 3.02. Yes, sir. Okay. So let me go ahead and take y of 1 real quick. It's going to plot R4, but the first plot, let's just change y of 1 real quick. I'm going to get rid of the exponential. Okay. And we're going to just go ahead and comment this out temporarily. And let's run that. Um, so, hmm? Oh, I did it. I did it to y1. I'm sorry. Didn't mean to do that. I meant to make to do it at y. Where is? Oh, y is all the way up here. No matter. I did it here. So, if you look carefully at the upper right-hand side of this, this is u of t minus u of t minus 2. There's a factor of 2 somewhere that's bothering me. Let me see. T1. Yeah, because I multiplied T1 by 2. I needed to do it at the other place. I apologize for that. Let me go ahead and do that. Control Shift R and do this where I intended it to be. Okay, a little bit of a hiccup on my little example here. I should have done it here because there's a 2t that happens down here that kind of was measuring my function. All right, so let's call this y. And this is the one that I should have blocked. Okay, so use step of t1 minus use step of t, and it should not be t1, it should be t. Okay, uh, t minus use step of t minus 4. Okay, and let's do that one. Okay, that's much better. Notice that what u of t would have done, it would have been 0, and then at t equals 0 would have gone up to be 1. Now, because we're delaying it by 4, right? Now that you delay it by 4, at 4, we would have had u of t go from 0 to 1, but there's a minus sign in front of it, right? So we have minus u step. So now what did we do? We flipped around the x-axis. That's exactly what we did. So now you're subtracting, and now you're subtracting 1 minus 1, and that's how you end up with 0 after 4. So you get the square signal by subtracting 2 unit steps, right? And one of them has to be delayed with respect to the other. And that delay determines how wide uh, this rectangular uh, waveform shape is going to be. Okay. Now, let me comment that out and actually put the real signal that, uh, oh, it just, sorry, I hit a command that kind of changed the window. Sorry. What I want to do is I want to comment this out and, uh, and that's not what I wanted. Oh, there we go. So putting it back to where it was original, where I'm multiplied by the absolute value of the exponential, right? All the way back to here, right? So now you see the original y of t, and we know that it has this shape because we know what the difference of those 2 unit step does. Uh, Here's a time compressed one, right? That's the upper right hand side. The time advanced one, we roll this one back by 2. And then this one actually flips the signal, compresses it, and then it advances it by 2, right? I need you guys to convince yourself that that's what's happening in the bottom right-hand side of this. Again, you're compressing it, you're inverting it in time, and then you're advancing it by 2, okay? Convince yourselves of that. All right. So getting back to the slides, I believe in the slides we have another exercise. That's correct. Um, and in this one, what we want to do is we want to take a periodic signal. We're going to generate, right, one period. And then after you generate one period, we are just going to replicate it to create our periodic signal. We said we could do that, right? So if I take a periodic signal and I delay it by t, and capital T in this case, and capital T is the period, I just get the same, then I can create a periodic signal of a period capital T, all right? And that's pretty much what we want to show with this last octave example. Um, and again, it's not super complicated. It's not a code. A lot of these exercises, most of the lines of code here is plotting, right? It takes quite a few instructions to sometimes plot things and make them look nice. Okay, but let's just go ahead and talk about this really quick. Let me see. We open this one. That's and this is example periodic function. Let's go ahead and open that one. So actually, we're going to do the periodic function, then calculate the powers and power and energy, right? So we'll calculate the energy and the power within one period. Okay, this is a power um, signal once you make it periodic. If we did not make it periodic and we allow the signal to go to 0, then we can talk about it as an energy signal. And we just want to show you guys how to calculate both, right? Again, a lot of the important things in this signal happens um, within the few first lines. Uh, Again, we're going to establish our time vector, and here's our signal vector. Let me go back to that nomenclature. Um, Sometimes it's a good thing to separate things so that create variables for them. So dt is nothing but that uh, time interval or sample time. We're going to start calling it all the time. From now on, it'll be the sample time. That's what we were calling epsilon when we did the vector discussion. Uh, we established a period or capital T for us, which is going to be 6. How many times do we want to generate the signal? In this case, m equals 3, and then our time vector. Okay. And here's the signal. If I did nothing else and I plotted that, I would get everything of the signal all the way up to 6, right? Which would be just one period of the signal. Now, in order for me to get it multiple times, what I do is I'm going to declare or initialize a time vector and a y periodic vector. That's just declaring them, making them empty, okay? And you can put comments to these things so you know what they are. I kind of neglected to do that here. And then after that, all you have to do is notice how we say that time equals what time was originally. This is why we have to initialize it, right? But so when you go first time through the loop, you need to have time. And then you're going to add I times the period plus t. That's that vector, right? We're going to add that times I, right? Which for I equals 0, you're just adding the vector itself. Next time around, the vector that was there plus capital T, and so on and so forth till you go through the whole for loop. And every time you do that, what we do is we take y periodic and we append y to it. That's what these things are doing, right? You take whatever the prior vector was and you append the other one to it. It's a very clever way of doing it. And this is how you create the periodic signal. And there we go. And there's your periodic signal and how we create it. If you like to, you know, sort of break this down and try different things, experiment with the code a little bit. Again, it's not very long and it's actually already posted to Canvas. With that, thank you for attending our class today. Next time, we will talk about orthogonal signal, correlation of signals, Parseval's theorem, and then Fourier series.